All right. Okay. How about we get started? How's everybody doing? Okay, I see all the blue sticky notes and some thumbs as well, so that's great. Thank you all for coming. This is a great pleasure to share some knowledge with you all on network analysis and stuff. So what I want to do today, we're gonna explore network analysis fundamentals, right? What we are going to do is to understand how to think through network style data. What we're not going to do is learn how to apply network analysis to specific problems in depth, all right? So in other words, this workshop, this tutorial, is really about the fundamentals of network analysis. Now, we will be using one Python package, and that's NetworkX, so I hope everybody has that installed and such. And NetworkX is a great package for prototyping and exploring network analysis concepts, though on a small scale, though I wouldn't recommend it on a large scale. Nonetheless, these concepts transfer over if you use other Python packages. All right? So now, before we get started, I want to very quickly share with you how this workshop is going to go. There's going to be a lot of hands-on coding activities. I'm actually going to minimize the amount of time I'm talking up here and blabbering and stuff like that, and I want to maximize the amount of time that you guys get to try implementing things on your laptop. Now, because of this, I'm hoping to encourage you all to talk with your neighbors and pair code, especially if you have trouble with some of the algorithms and stuff. And if you do have trouble, don't worry, because some of these things, when I was making the material, it took me plus another MIT undergrad to work together to figure out how to implement some of these algorithms that we're going to work through. All right? And so don't worry if you're encountering trouble. This workshop is meant to be an intermediate level Python workshop, and so I do expect that you do have at least some basic knowledge of Python and list comprehensions and dictionaries and data structures and stuff like that. But it's going to be fun. It's going to be challenging, but it's going to be really fun. And it'll be made even more fun if you start networking with one another, pun intended. All right. So I want to start with a very quick quiz here. If I give you this list comprehension, can you infer what the data structures involved are? Do we have answers? Raise your hand if you have an answer. Trevor. Yeah, okay. This was not meant to be a trick question, and that's exactly it. So my favorite things is a dictionary, because we have the dictionary accessor syntax over there. And my favorite things is something we can iterate over in a list comprehension, right? So my favorite things would be an iterator of some sorts, and it's a container for these dictionaries. Cool. Now, I just want to make this clear. You'll be seeing a lot of this programming pattern in this workshop, right? List comprehensions are going to be a big thing. So I'm assuming everybody's done the check-end thing already as well, right? Just want to do a final check. Everybody's okay with the environment. So some of you may have issues installing SciPy and stuff. Don't worry about it. At that point, we'll do pair coding for those 3 little cells that involve SciPy code. Okay, so let's go into basics. Networks. Networks are also known as, in mathematical and CS terms, as graphs, all right? And so networks are actually very simple, high-dimensional structures. Networks are made up of nodes and edges, and typically we represent them as circles and lines, right? And so nodes are usually the things that you're interested in, and edges are the relationships between the things that you're interested in. So one thing I hope that you'll take away from the end of this tutorial is that, yes, you've got data points, right? You've got your nodes, and those are your data points. But a more interesting thing that you can start to investigate is the relationships between those data points. And a network or a graph is a great way of modeling and storing these relationships. Now, if you, this is a quote that I took from a seminar talk by John Quackenbush at the Harvard School of Public Health. And the heart of a graph lies in its edges and not its nodes. And really, it's because the edges give rise to what's interesting about a graph, and we'll start to explore that during today's tutorial as well. So there are two types of edges, two types of graphs, or two types of networks, generally speaking. There's the directed and undirected network. So I want to put this question out there. What examples of networks do you guys know? And can you tell me whether they are directed or undirected?
For that, Twitter is a type of network.
Yep.
Consider it directed because I follow somebody, so there's a direction to that.
That's right.
Not necessarily following that.
Yep, exactly. So Twitter is an example of a social network that is a directed graph, and it's represented most naturally as a directed graph because the relationships can be unidirectional and are not automatically bidirectional. Right. What other graphs, what other networks are there? Cities and streets between them. And what would this be? This would be a... That's right, because the most natural way of representing a city and a road network between cities is as an undirected graph. And so the nodes are the cities and the roads automatically allow for bidirectional travel if the lanes are painted the right way. And so we allow for, so these would be undirected graphs. Anything else? Air traffic network. What would that be? That be directed or undirected? Anybody want to take a stab?
I read in the notebook it's directed.
It's directed, and the reason is?
Well, I guess because the allowed flight paths are probably one directional. You can't just pick a side which you fly from one network to the other direction.
Right, and so from the domain experts' standpoint, right, depending on how we look at flight networks, it can be directed or undirected. From the airline's perspective, they are directed because you can fly one direction, but you may not necessarily have a return flight available unless you decide automatically to bake one in. Whereas from a larger standpoint, if we're doing, say, modeling of transportation networks across the world and we're like a operations research type, we might not want to bake in the definition of a direct or undirected. We might not want to bake in the directed definition because that would complicate the problem a little bit, right? So yes, those are examples of networks, and networks lie everywhere inside our daily lives, and that's why I think it's an important thing. I myself use networks in my graduate school research, right? I study the flu, and so we look at patterns of transmission, right? And networks are a very natural way of representing this kind of data. So at the end of this tutorial, what I'm hoping you'll take away are the following things. One, you can use NetworkX. I'm hoping to equip you with the capability to use NetworkX. And that's because NetworkX is a nice and simple package for getting started with network analysis. Two, I'm hoping to share with you how to do basic algorithms on graph-structured data. And through that, communicate this idea of how do we think through a network, network-structured data, and derive insights from it. And the final thing is, how do we do network statistical analysis on networks? And this is sort of an introductory new material that I've put in for this year's PyCon. And it is a bit of a testing thing, so I'd welcome a lot of feedback on that to see whether, how well it was conveyed and stuff. And more broadly, data science is all big and hot, and we like to think in terms of our data matrices, which are rows, and our features, which are columns, but I want everybody to start thinking through a different way of looking at it, which is how do we think through the relationships between the rows, not just the rows itself. All right? And so with that, let's get started with the hands-on stuff. We're going to start with Notebook 2, which is a very lightweight, I hope, introduction to NetworkX and its API. All right? And then Once we get past this, we can go and dive into the fun stuff. So if you could open up NetworkX notebook number 2. Oh, I forgot to mention. You'll notice there are always two, for most of the notebooks, there are two versions of the notebooks. There's the instructor version and the student version. The instructor version, obviously I'm using that. I'm hoping you would use the student version because it contains all of the stuff that I've implemented. I've blanked it out or put skeleton code there for you to try implementing. Now, if you ever get lost in one of those exercises, please feel free to open the instructor version and take a peek. I won't be offended. It's my way of saying, my way of trying to help everybody catch up with what's going on, all right? All right, so if you could open up notebook number 2 and run that first cell, we're going to very quickly go through the NetworkX API, all right? And so let's go through this. So in NetworkX, everything is represented as dictionaries. Nodes are a dictionary, and they are a dictionary of where the key is the node, and the value is another dictionary of node metadata, or in NetworkX terms, node attributes. Likewise with edges, NetworkX stores everything as a key of one node, being one node, the value being another dictionary where it's another node, and then the value of that other dictionary, that internal dictionary, nested dictionary, is a set of edge attributes, all right? So when you look at how you access data, you can either do iterations over lots of dictionaries, or you can you can do iterations over dictionary key value pairs, or you can do direct dictionary accesses, and we're going to look through that by the end of this notebook as well. So in order to keep things simple, for the first few notebooks, what I have done is I've created this synthetic social network, which is an undirected graph. We're keeping everything simple. We're not going to talk about directed graphs or anything. We're going to use undirected graphs and small graphs to look at some of these algorithms and the NetworkX API. And so what we're going to do is we're going to try exploring this graph with the NetworkX API so you have a bit of a warm-up. All right? So please run the next cell below, which is the read gpickle cell, and that will load the graph from disk into memory. And then we're going to look through the structure of the graph very quickly, all right? So first off, we can ask the question, how many nodes are, or what nodes are present inside the network, all right? And so the API call for this is g.nodes, right? And what it will return is, can anybody tell me what the data structure for this is? It's a list of integers, right? So it's a list of integers. And so this function call returns a list. And so very quickly, can you try that the first warm-up exercise? Can you write a single line of code that returns the number of individuals represented inside the graph? And please take down your blue sticky notes. All right, take down your sticky notes, and then when you're done, stick the sticky note back up. And by the way, if you're done early and you want to move on and not listen to me, go ahead, no problem. All right, and what we'll do is we'll wait for about 80% quorum, and then we'll move on to the next thing. Don't forget the blue sticky notes once you're done. Okay. So how do you get the length of the list? That's the number of nodes inside a list. That's the number of nodes inside the graph. So all right, so let's not spend too much time on this one. This is the length of the graph by doing len g of nodes. And I'm also going to show you an alternate way. If I do len g, that also gives me the number of nodes that are present inside there. These are simply two alternate ways of doing the same thing. All right. We can also query the graph for what edges are present inside the network, right? And so we can take a look at, so if you do g.edges, this will be this is the API call for figuring out what edges are present inside there. So as you'll notice, there's a node list and there's an edge list, essentially, right? And so what's the data structure of this guy? It's a list of 2 tuples, right? And in which the first element in the tuple is one of the nodes in the edge, and the second element in the tuple is the second node inside that edge, all right? So very simply, can you run this next exercise over here? All right, how are people doing? Good. Don't forget to put your blue sticky note up. I'm just going to look very quickly across the room. Okay. So did you all get 48? Len g dot edges, right? Simple thing as well. So please take down your sticky notes. Okay, so if there's metadata inside the graph as well, actually, let me just see here. So if there's metadata that's inside the graph, you can take a look at the metadata as well by passing in the data equals true keyword argument into the g.nodes or g.edges function. So if you run down, you'll see that, right? And you can see I have individual 0, 1, 2, 3, 4, 5, and the age and the sex of that individual over there. All right? Whoops, what just happened? There we go. So what I want you to try next is to write a block of code that grabs out the number of males and females that are represented inside this graph. There are a number of ways you can do it. If you're not too comfortable with list comprehensions, write a big for loop instead. If you're comfortable with list comprehensions, you may want to tag on the counter object from collections as well, and give that a shot. So give that a shot. And when you're done, please put your blue sticky notes up there. And if you're encountering trouble or you want to interact with people, I know this is a programming conference. We're all a bit nerdy and don't really want to interact with people, but pair coding is always fun, right? Pair coding is always fun, and we're talking about network analysis, so go network with your neighbors. Have fun networking with your neighbors. And don't forget, if you're having trouble, put a red sticky note up and I will come by. If you're done, please put your blue sticky note up on the laptop. And for those of you who have finished already and you want to move on to the next few exercises, please go ahead. See how many do we have? Okay, looks like we're at quorum. So my own implementation is, it's 15, sorry. Later on, we add some nodes, and so it becomes 16. So my own implementation is a list comprehension, and I iterate over the two tuple, right? It's a two tuple, so I can do the tuple expansion and do nd and g.nodes. And then I grab out this guy over here, and then what this list comprehension gives me is a list of male, male, female, 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 male, 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 blah, blah. And then I do a counter on that, and it'll do the counting for me. All right? So with that done, we can also do edges, like I was mentioning earlier. In this case, it's a list of 3 tuples, in which the first 2 are the nodes involved in the edge, and the third is the dictionary of attributes. So if you could try the next exercise, can you figure out the range of dates during which these relationships were forged? So in other words, find the minimum and the maximum of these edge attributes, the dates. And take down your sticky notes first, unless you're already done, in which please go on. I'm noticing this is a pro crowd. This is a very competent crowd. Okay. If you're done, don't forget to put your blue sticky note on your laptop. Looks like we're at quorum. So I think I put in some skeleton code there, right? So you'll notice the list comprehension pattern one more time. And in this case, because g.edges returns a 3 tuple, I can do the tuple unpacking this way, and then collect all the dates and ask what's the min and the max, right? Because datetime objects, we can compute mins and maxes. They're comparable. Okay? People okay so far? Looks good. All right, so with NetworkX, there are functions that allow you to add nodes and add edges into the graph. And so, please take down your sticky notes for this next exercise. So what I'd like you to do now is, based on this exercise prompt, try adding these new individuals and new edges into the graph, right? I've provided some skeleton code that you can model off, or some example code that you can model off. And then when you're done, don't forget to put your sticky notes up. Don't forget your sticky notes when you're done. I see a red flag. Looks like we have quorum again, and so if you should see something like that, all right? Now, I did get a question just now from Trevor, right? What happens if you add in another node that is the same, same label, say number 31, but you have different metadata? Oh, you haven't tried it? OK, all right. So network X silently overwrites stuff, right? So if I do g.add node 31, age 22, et cetera, and I change the age in a separate call, that should change, the node metadata as well. And I'm just going to very quickly show that. So notice here, at first, I added a node that was number 31. I've changed the age here. It silently overwrote it to be 25. Question? Yes, you can write a custom. So this would be custom implementation, right? So for example, if I were to iterate over a node list, right? And I say I could do if the node exists, if g.has node this guy, raise exception or something like that. All right, so that you can capture all of these duplicates. Okay, now if you ran that test stuff down below, that would be good. A little thing on tests that I have started to really like is you should write tests for your applications, and you should write tests for your data, right? What do you expect about your data? Are there missing cells? Are there negative numbers where there should not be? That sort of stuff. You should be looking out for that. There's a really good package actually called OnGuard. It's for data analysis. It's defensive data analysis, and I think it's worth checking out. ENGARDE. Okay, so you would have noticed that over this API warm-up thing, we've used a lot of list comprehensions, right? And I want you to get used to using list comprehensions, stuff like that. It really makes, you can use list comprehensions to query graphs in Network X, and it's a really compact way of doing it. Now I want to just very quickly for the next 2 or 3 minutes show you different ways of looking at a graph. We've all done this sort of abstractly in memory, but nothing beats visualization. So what NetworkX offers is a few API calls for drawing graphs. You can draw nx.draw. You can call nx.drawg, and you'll get something like that, right? And you'll notice that the layout is never the same. Graph visualization algorithms. There's a lot of work that goes into it, and typically there's a random component into this because the XY positioning of the nodes really doesn't matter. It's the relative positioning and how they're connected that matters more, right? Now, if your networks are small enough, you can add this function, add this keyword argument called with labels, and then you can get the labels of those guys, and so you can immediately see, which nodes are not connected to anybody else, or which are highly connected nodes and stuff like that. Now notice though, you take something like this guy, and at 30 odd nodes, it's starting to look a little crowded. And I'm wondering how many of you have actually seen those hairballs, right? Those hairball network visualizations. I'm partially on a mission to eliminate hairballs from network visualization. And so I want to show you a few alternate ways of visualizing data, network data, at a larger scale. So one way we can do this is by using a matrix, right? And so a matrix representation looks essentially something like this guy over here, in which I have zeros everywhere. I initialize with zeros, and then I put ones wherever two nodes are connected. So it's node on the x-axis and node on the y-axis. I put ones there. Now, if you have what they call a weighted graph, in which there's a quantity that's associated with each edge, you can start coloring the intensity of those cells by the quantity of that edge weight. This here is an undirected graph, and so you can see it's symmetric around the diagonal. All right, the top half, the top left triangle is the same as the bottom right triangle. If this was so this is true for an undirected graph. Sorry. If you have a directed graph, it may not necessarily be symmetric, right? Because one individual here, 15, can be connected to 5, but 5 might not necessarily be connected to 15. All right, so that's another way of visualizing it. This also happens to come straight off the adjacency matrix, which is another way of representing the edges. Here is another way of visualizing network data. Now, if you go below, you'll see what we call a Circos plot. And a Circos plot essentially is like it's like a very elegant condensed version of the matrix view of a graph, right? So all of the nodes are listed in the circumference of the circle in whatever order you specify, and the edges are drawn as Bezier curves in between them, and that makes for a very nice visualization. And you can see immediately nodes 5 and nodes 19, for example, I think, or 17 or something. These guys are the ones that are not connected to any other node inside the graph. We can also look at hive plots, and hive plots are another nice rational way of visualizing network data. It might not be 100% clear on the projector screen here, but if you look at it inside your notebooks, you can see what we can do with hive plots is we can group the nodes by some particular grouping of their metadata, for example, and then we can draw lines between the two groups, which is on the right-hand side in your notebooks, and we can draw lines within a group simply by cloning the axes and drawing lines between them. All right? And so that's another nice and rational way of visualizing network data that doesn't involve big, massive hairballs, which are uninterpretable and such and such. All right? And so immediately what becomes clear here is that there are a lot of connections in between groups, and there are fewer connections, or it looks at least visually like that. Right? We can always do statistical tests on that later on. Okay. So those are some ways of visualizing network data. All right? And so that is Notebook 2. We're going to conclude Notebook 2 here. Basically, the idea here is get familiar with the NetworkX API and get familiar with list comprehensions. We're going to start with the really fun stuff in Notebook 3. So I'd like to get everybody to open up Notebook 3, please. And run that first cell as well. And oh yeah, please take down your sticky notes. Yeah. Okay. Yes, question?
On the last two visualizations you showed, are those consistent every time you replace them?
That's right. And that's because we've specified the order in which the nodes show up. Before we move on to notebook number 3, do we have any more questions? Yes?
I'm trying to understand. If you put a line down horizontally that, it's the same nodes going up as we flipped it over to the other.
That's right. So initially, if we wanted to look only at the edges between groups, we'd put one line for the blue, one line of nodes for the red, and we look at that. But if we want to simultaneously visualize the within group stuff, we clone that axis and expand it out a little bit, right? And then we draw lines between them. All good? All right, let's move on. So with graphs, a really fun thing is to look at the structure of a graph, right? Looking at the nodes and edges, those are kind of okay and interesting, but the more interesting stuff is the structure of the graph. And one of the cool things, one really useful thing, that we can do is we can look at nodes that are important. And nodes that are important come out as important because of the way that they're connected to other nodes. So we're going to look today in Notebook 3, we're going to look at two things. Before the break, we'll do part of one of those ways of looking at importance, and after the break, we'll continue, all right? So break is at 10. So if we have a network of people, how do we identify what's important? Like I was saying, connectivity is a good metric, and we can use neighbors to figure out what's important, right? Because if I'm connected to other people, I might be a really big hub inside this social network, or I might be a super spreader if I'm a carrier of an infectious disease, or I might be a big influencer in my social network, right? LinkedIn has all these influencers, which are highly connected nodes, essentially, right? And they can broadcast messages out. So how do we identify these influencers? Well, one way we can do this is to look at the number of neighbors that influencer has. So network X lets us do this by giving us a g.neighbors function, and we pass in the node ID or the node string, and we can get back the list of neighbors. So for example, if I run this cell, g.neighbors 7, it will tell me which other nodes are connected to node number 7. So what I want you to try now is to create a ranked list of nodes by their importance as measured by the number of neighbors that they have. So give that a shot. And when you're done, don't forget to put your sticky notes up. Talk with your neighbor, because we're on the neighbors portion now. Don't forget your blue sticky note when you're done with the exercise. And if you're done, like I was mentioning over and over, you want to continue on with the later exercises, please go ahead. Actually, if you are done, you should find that individual 19 is the most connected. Sorry, there we go. Individual 19 is the most connected. There are two ways of doing this. I've used a bit more, slightly more advanced Python, in which we use the lambda function and the sorted and stuff like that. If you did it as a plain old for loop, and then you sorted a list at the end, totally okay there too as well. All right? There are many ways of doing this. This is one of those things where I think with a Zen of Python doesn't really show up, and there should be one and only one way of doing things, but with the graph algorithms, there are lots of ways you can do this stuff. Okay, so if you get something like this, you should see that we can sort, essentially, a list of nodes, and they're sorted by either the length of the neighbors list, or they are sorted by the g.neighbors, the length of the g.neighbors function, right? There are two ways of doing that. All right? Are people okay with that? Okay. So what I'd like you to do next, so my bad, let me backtrack a little bit. So the number of neighbors is directly related to the degree centrality of a node, right? And the degree centrality is one of those metrics that's used to determine which individuals are important. So NetworkX provides the functionality for figuring out what the degree centrality of every single node is. And the degree centrality is essentially the number of neighbors that a node has normalized to the number of neighbors that it possibly could be connected to. All right? So if you run this function, you'll get a dictionary in which the node is the key and the centrality metric is the centrality metric is the value. Now, how many ways are there of computing the degree centrality? There are actually two ways. The number of possible edges, the number of possible neighbors that I could be connected to depends on my graph definition. If I'm allowed to be connected to myself, that is a different degree centrality than if I were not allowed to be connected myself, right? And so there are some networks in which it makes sense to say the node can have a self loop, and that's, say, for example, a bike sharing network where, if I'm modeling the transportation, the bike rides, sometimes people will start and end at the same node, whereas, things like social networks make no sense to have self loops inside there. And so the definition of the degree centrality would differ. Now, with NetworkX, if I'm not mistaken, they do not count self loops, or they do not allow for self loops inside here. Oh, my bad. Sorry, no. They do allow for self loops. Self loops are allowed, and so the degree centrality includes edges that connect one node to itself. All right? So this is meant to be not too difficult of an activity, but I want you to create a histogram of the degree distribution, as well as a histogram of the neighbors distribution, and just simply for yourself, convince yourself that these two essentially are related, and that they're related. So don't forget, stickies down, please. And if you know the Matplotlib API like the back of your hand, go ahead, go fancy with it. If you have Seaborn installed, go ahead, go fancy with it as well. Don't forget the sticky notes when you're done. I'm going to flash up the first plot and the code that's needed. I did notice that this line, in an earlier iteration, this line is a little bit verbose, so we could do something like, so instead of this line, we could do nx, cast as a list nx.degree centrality of G, the values over here. So in other words, we have the values inside, the values of this dictionary are cast as a list. I think we should get the same thing. There we go. That's a little bit more compact. And that should give you a hint as to how you do this for the next one. And if you're done with at least the first and the second, can you please put a sticky note up? All right? Just those two are sufficient. Okay, how are people doing? So one guy over there did mention that if you change the visualization a little bit, you can take a look at you can put the nodes on the x-axis, and you can put their degree centralities on the y-axis. That becomes like a bar plot of the degree centralities or the neighbors, and that's an alternate way of visualizing the distribution of degree centralities. All right? Okay, looks like we have some quorum, so let's move on. Basically, the idea that degree centrality is a measure of importance that's the basic idea that I want to sort of convey to you. And so degree centrality and the number of neighbors are related by the mathematical definition. And the way that you would use degree centrality is essentially to look for hubs, right? Hubs in which information is easily spread out from that one node to the other network, right? And so information, so LinkedIn influencers, like I was saying earlier, or infectious disease super spreaders, you want to target the hubs for preventative vaccination and stuff like that. Transportation networks, you don't want your hubs to go down, right? And you can measure all of that by looking at the degree centralities. All right, so it is 6 minutes to the break. I want to give everybody a little bit of advantage in going for food and stuff. So I'm going to stop here and ask if there are any questions. And if there are none, we can all just go for a break and stuff. Do you guys have any questions so far? All right. Okay, looks like everybody's doing fine so far. Let's go for the break. I think if I'm not mistaken, the break is 10 a.m. and it should be about like it should be about 10 to 15 minutes. So, let's come back at say 10:15, if everybody's okay with that. So, we left off at the spot where we said a measure of importance is the number of people that I'm connected to, right? And the examples were hubs or super spreaders or influencers. But there's another way that we can assess the importance of a node, right? And that way of measuring importance is related to how many paths go through it, how many shortest paths go through it, right? So an example is something like this. If I'm going to spread a message, and I'm not going to do an internet broadcast, I'm going to do it by sneakernet. I'm going to have one person pass it on to another, and so on, right? How many times does, how would we find out which node is an important node to pass through, right? Because that would be an important node that the message, if we started at any one place and ended at any other place, that message would have to, over all of these multiple tries, that message would have to pass through that particular node, right? And so finding the shortest path is one way to do it. And by the way, finding the shortest path between any two nodes and figuring out what nodes go through are present inside there is one way. So sorry, let me backtrack. If we want to know what's important, we figure out which nodes are on the shortest path between any pair of other nodes. At the same time, shortest paths algorithms are also immensely important, right, for message passing and stuff like that. And so what we're going to do here is we're going to look at how we can implement one of these shortest path algorithms, right? So one way that we talk about this, so for those of you who have learned your CS all the way up till 4th year undergrad, you would have implemented a breadth first search algorithm, and essentially that's what we're going to do here, right? If I want to figure out how many steps it takes me to go from one node to another, I can do a breadth first search. I can search through my neighbors, and then search through my neighbors' neighbors, and neighbors' neighbors' neighbors, and so on recursively until I reach my final destination. If I wanted to find the shortest path between those two nodes, I could also still use the breadth first search algorithm. And so this is where it comes pretty handy. So I've put the pseudocode or the algorithm description inside the notebooks. What I would like you to try to do, this is where the challenge and fun starts, is to try to implement this where it takes in a graph in two nodes and it returns, well, I want you to try this next challenge exercise, which uses the breadth first search to determine whether a path exists between two nodes or not, all right? So I want you to give that a shot. This one is a bit challenging, and so if you want to talk with your neighbors about this problem, please absolutely do so. It may help. I'll back up and put the pseudocode up as well. It may help also if you have paper and you're drawing on how that works and how the algorithm works and such. So the approach sort of is, I'll start at my starting node, ask what neighbors are there, visit that next node, visit one of those neighbors, ask whether my destination isn't, sorry, ask whether that neighbor is my destination. If it isn't, find more neighbors of that neighbor that isn't myself. So you have to keep track of which nodes you've already visited as well. All right, and then continue on iterating over those nodes until you find your destination. And if you're done, don't forget to put your sticky notes up so that I can tell. We'll go for another 5 minutes, just 5 minutes more. And if you're done, you want to sneak peek at what's later, please go ahead. So let's see. I think we've got some degree of quorum here. Most people have finished this exercise. So the idea, the logic I had gone through earlier on, it was so I iterate over each of the nodes. Now some of you did, iterate over each of the nodes and then ask whether that node is the destination. If not, move on to the, tag on the neighbors of that node onto this list of nodes that I have to visit, right? Some of you did point out it's a bad practice to remove a node from a list that I'm iterating over. Absolutely correct. Absolutely correct. I did this on purpose for this notebook, and this is because sometimes I encounter audiences that are a bit more elementary than what I've seen here, and so for them, this is sort of like the easier version to wrap their head around. It's something that I found. All right? But yeah, never do this in your production code. All right? Okay, and if you do the tests, there should be no paths between number 18 and number 5, but there should be a path between 29 and 26, and so that should be okay. All right. Now, I did ask you to implement an algorithm that's already implemented in Network X. Part of the reason is I think it's a useful activity. Even if you're already experienced with writing graph algorithms and stuff, it's still a useful thing to recap. And I think that process of thinking through a process on a graph is really the important thing that I want you all to take back here. If you're looking through graph structured data and you want to write a special algorithm that's not implemented anywhere else, typically you do have to take into account the fact that you as the human can keep track of the entire graph in your memory, but the computer itself, when the computer doesn't have that, right? You have to explicitly, programmatically ask it to do things that traverse the graph, right? And graph traversal is extremely, it's an important thing to take back from today. Okay, so NetworkX actually does have, like I was saying, its own has-path, I restarted, never mind. It has its own has-path algorithm, and if I restart the whole notebook and run it through, this would show false. So the next thing that that's implemented in NetworkX is also this shortest path algorithm, in which not only will it ask if there is a path between two nodes, it'll also tell you one of the shortest paths between those two nodes, right? It won't tell you every single one of them, but it'll tell you one of them, right? And so, for example, between node 4 and 14, there could be multiple paths that are of length 4, right? I have to, of length 4 nodes, or in other words, 3 hops between 4 and 14. But of course, like I was saying, it'll only report back one of them. And so what I want you to try to do is this next exercise over here. That is to write a function that takes the, so what we're doing now is we're composing these elementary functions that NetworkX has and putting them into like higher order functions that we can use to query and extract information from the graph. And I think this is also a very useful thing to try. So I want you to try now is this exercise here, in which you extract the subgraph, that is the set of nodes that are involved in the shortest path between any two nodes, and then draw them to the screen. All right, so give that a shot. This one shouldn't take too long. Oh yeah, if you're done, put your sticky notes up, and if you're not done, please take them down. My bad. Okay, how are people doing? As a hint, so we're saying extract the edges, but if you do g.subgraph and a list of nodes, that automatically gets the edges out as well. The edges that are connecting those nodes only. Right, so that means extraneous edges that don't involve those nodes will not be included. Okay. So notice I'm making use of the hasPath function to first check to make sure that the graph actually has this path available. And then if it does, because you can get an error where it returns nothing, and that's a weird scenario. So you want to check, defensively check for everything, all edge cases. So then we have the shortest path between those involves a bunch of nodes, and then we pass that into g.subgraph, and then we get the new graph, which is that. And then at the end, we draw that graph to draw out that graph. All right? In the meantime, does anybody have any questions so far?
Any reason why you didn't just make an else statement? Why you didn't get something false?
That's true. Should be, because there's only two scenarios, right? I was just being explicit there. But yeah. Good catch. All right. Okay. Yes, question. Pardon me? So hasPath, according to the network X, so the question is, what if hasPath returns something different, right? So hasPath in network X only returns a Boolean. It's true or false. So we can always use this to check. Okay? And actually, in the interest of being more concise, we can even take that out. If nx.hasPath, you don't even need the double equals true. Question? That's right.
So if there's other connections in that subgraph, would that be displayed as just coincidental that there's only a single path?
That's right. So yes. So if there, say, for example, was an edge between this node over here and that node over there directly, then yes, that edge would also be extracted. It would not just be the path along that, right? That's what g.subgraph does. Okay. All right, we're going to skip this next exercise because I think it's more about plotting things and more of the same. So if you'd like to go back home and try that out, welcome to do so. What I'm going to do is we're going to take a look again at this idea of importance, all right? So one way of looking at importance was the number of neighbors. Another way of looking at importance was how many times does a message if passed between any pair of nodes, have to go through that particular node, right? Or in other words, how many times is that node on the shortest path between any pair of other nodes? So can you think of a scenario where a node might be really important as measured by the degree centrality, but not so important as measured by the, sorry, reverse it. Can you think of a scenario where a node might not be important as measured by the degree centrality, but really important as measured by the betweenness centrality? Is there a scenario?
So, suppose internet traffic.
Yep.
There might be a hub between a lot of different locations, say in the middle of the continental U.S., but to get a message to Europe, you have to pass through an undersea cable that comes offshore in Virginia. So all the messages through there.
Right. So one example there that Mikhail was talking about was you have this one node that acts sort of like a bottleneck, right, for message passing. And everything has to go through there. And that node itself is maybe only connected to one other thing on the other side and maybe two other things on this side. But because everything has to pass through there, it's not very important as measured by degree centrality, but it is very important for message passing as measured by the betweenness centrality. So in a more abstract sense, you can actually look at something like a barbell graph, something that looks like this, right? A barbell graph, essentially, if you take a look at the barbell graph, this guy over here has a very high betweenness centrality, but has a very low degree centrality, because it's only connected to two things. But every messages that have to pass between these two communities of nodes have to pass through that node all the time, that middle node all the time, right? And so that's one example where you can have different metrics of importance, and they don't necessarily concord for the same node, all right? So are there any questions about this before we move on? Okay, great. So let's go on and let's explore graph structures in Notebook 4. So I'd like everybody to open up Notebook 4. Notebook 4, I think, is one of the most fun notebooks inside this series here, because Notebook 4 gives us there's a lot of fun algorithms, and it's also got a lot of good usage applications outside. So if we look at, sorry, let me just get this up and running. Okay. If you have a social network and you have a clique is one very interesting structure in a network. You have a graph, you have a subgraph of nodes in which every node is connected to every other node in that subgraph, right? It's essentially what we would think of as a real clique in real-world scenarios. The smallest clique that you can have, now, here's a question for everybody. What is the smallest clique you can have? Right, the smallest clique that you can have is an edge in which everyone's connected to everyone. What is the smallest complex clique that you can have that is not an edge? It's therefore a triangle, right? And so triangles form the foundations of a lot of interesting graph structures. And that's what we're going to look through today, all right? So so triangles and squares, squares are a special case of triangles, and I'll get to that in a little bit. You can think of them as actually four open triangles. But what we're going to do first is we're going to look through looking for triangles in a graph. And where does this get applied? If you think about friend recommender systems, right? Essentially, all these friend recommender systems are about closing triangles, closing open triangles. I have A knows B and A knows C, but B is not connected to C, then we can start recommending that B get connected to C, for example, right? And that's how closing of triangles becomes really useful. And actually, this is exactly how LinkedIn began its connections recommendation system. All right? So what we're going to do is we're going to implement a few algorithms that look for triangles and look for open triangles, right? And this is where it gets really fun. So the simplest clique, as I mentioned, was a triangle. Simplest complex clique is a triangle. And so what I've provided for you inside your notebooks, this should not be an exercise there, is a piece of code that asks whether a node is present in a triangle relationship or not. So if we think through how we might do that, we can take advantage of graph traversal to figure that out. We can ask, if I start at one node, can I find a 1, 2, 3 length path back to myself? Or in other words, can I look for my neighbors, 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 including myself, right? Does my neighbors, neighbors, neighbor list include myself? If it does, then I am in a triangle of some sort. And that's essentially what this algorithm is doing here. Now, I've done this, again, in a very naive fashion. And you would want to do it, if you want to do more compactly with recursion and stuff, that's totally up to you. So Network X does implement a triangle function, and you can use that to look for nodes that are inside a triangle, and it'll tell you how many triangles that node is inside. So what I want you to try to do is to write a function then to take in one node and its graph and return a list of all of the other nodes that it's in a triangle relationship with, if it's in a triangle relationship. And if it's not, return just that node itself. Oh, my bad, sorry. Return a list or set of itself plus all the other nodes, and that's it. Don't return anything or throw an error if it's not inside a triangle. Of course, there's an alternate way. If I want to know if I'm in a triangle, then my neighbor's neighbors should include my other neighbors as well. That's another way of looking at it. And if you're done, don't forget sticky notes. At the end, I think I've also provided a function that, or a line of code that you can use to verify all the triangles that one given node is involved with. Once again, don't forget, if you're done, please put your sticky notes up. And if you're done and you want to move on to the further exercises, by all means, please go ahead. For those of you who are done, don't forget, verify your answer at the end. You should be able to convince yourself that you've only grabbed those nodes that are involved in triangles with one given node and not any other node that is its neighbor. I have functions down there, draw out the appropriate subgraphs. This problem is a little bit difficult, so we'll continue on until we get about 80% quorum. Don't forget the sticky notes if you're done. And if you're feeling lost, go ahead, take a look at the instructor notebook. No problem there. Over here, I'm flashing up my own answer. One possible implementation. Don't treat it as gospel. You know, it's one of a few ways of doing it. But really, the core logic here is I check whether my neighbor's neighbors, excluding myself, is also my neighbor. And that's the core of finding these triangles, right? Or like I was saying, that second other way of doing it is I take a path from my neighbor to that neighbor's neighbor, and I ask if there's a path back to me, right? And that's also another way of looking for triangles. Okay, shall we move on? Are people okay with this one? If you are okay, just give me a thumbs up. If you'd like a bit more, okay. I think we got quorum. Let's move on. Okay, so just to convince yourself, right, there's node number 3 is in triangle relationships with these other nodes, right? And you'll notice there is one open triangle over here. Can you guys see that one? It's 1, 3, and 6, if I'm not mistaken. 1, 3, and 6, right? And 1 and 6 are not connected with one another. Now, if we did add all of the neighbors of 3, you can verify that, you know, these other guys are in the triangle relationships, but 3 and 8, 3 and 8 is not part of the triangle relationships of 3. It's actually one of the open triangle relationships. So, like I was mentioning, friend recommendation is based on open triangles, and I'd like you guys to try your hand at implementing a search for open triangles inside the network. So give that a shot. So stickies down, please. Stickies down. And if you're running into trouble, talk with your neighbors. Talk with your neighbors. Okay, I see one sticky note. This one is challenging. I'll give ample time for this one. In the meantime, if you do have questions, I'm happy to answer them, unrelated to this particular problem as well. So for those of you who had questions, this question has come up a few times. Why is it that we get with the get triangle? Ooh, what's happened here? Why is it that with the get triangles function, I ask for number 3 to also be included? And the reason is because with that, what we can do is we can take that whole thing and we can pass that in g.subgraph of those nodes and then draw that subgraph to visually verify, right? You might or might not want to have 3 also included in there. That will depend on your application. People who are done, what do you all think of having them also walk around and see what questions people have. What do you all think about that? Go, no go? Okay, I'll leave that to you all. If you have questions, they're done too as well. You can also ask them for how they did it. Just out of curiosity, where are people stuck on this? Sort of, do you have a comment on where you're stuck right now? It's totally okay. Like this thing, by the way, I didn't implement this on my own. If you look at the pseudocode if you look at the code in the instructor notebook, for credit with another undergrad, MIT undergrad, they're really smart, these MIT undergrads, on we took a good half-an-hour session at the Blackboard figuring out this algorithm for ourselves. So where are people stuck? Sort of curious. Well, if you're stuck, you need some help, put the red sticky up. Don't forget, there's a red sticky note for that, and I'll come by. So for those of you who are done, I actually just thought of a challenge problem you might want to try. Try an alternate implementation that uses pairs of nodes, iterating over pairs of nodes. Now this is obviously very inefficient, but it's another way to think through that problem. So you can try adding another cell below and try iterating over pairs of nodes to see whether you can get the same answer. And so the logic for pairs of nodes is sort of, we share a neighbor, but we're not neighbors. Right? That sort of, and then you can ask whether a given node of interest is inside that triangle or not, and you can count. Right? So that's another challenge problem. I just thought of that one. You might want to give that a shot. But please keep your blue stickies up, because I want to know how far people are in. And again, if you're stuck, talk with your neighbors. Talk with your neighbors. Okay, so we'll give this problem just 9 more minutes, and we'll continue on at 11:30. Now, if you didn't finish this problem, though, just want to put it out there. If you didn't finish this problem, don't worry. It's totally okay. Like I was saying, sometimes some of these stuff you have to work with someone else to figure it out. We had to work with an MIT undergrad to finish this, Justin Zablansky, so big credit to him for helping me with that. Some of these graph algorithms are difficult. And there's always the instructor notebook if you're lost. Okay, I'm seeing a few more green stickies come up. That's great. Go down in the notebook and you check it against my answer. That should tell you whether you've gotten it right or not. In the instructor's notebook, that's right. Yeah, should match mine is 25 neighbors for number 19. Let's see, do I have this? Oh no, I don't. Let me, you can actually, you can also check to see, use the, oh, no, we didn't implement this function earlier on, which is check if these 3 nodes are in a triangle. But if you had that function, you can use that to check your answer as well, because none of those triplet nodes should be in a triangle involving each of those 3, right? So let's go back out here. Notebook. Okay. Let's see if there's a simpler one. Okay. If you're not done, don't worry about it. There's the instructor version of the notebook. You can check out the logic there. That was tough, right? Like I was mentioning, this is actually going to be the toughest thing that you're going to encounter in this workshop. Everything past this point is much, much easier. Now, there are 2 ways that you can think of, there are a number of ways that you can think through this neighbors problem. This open triangles problem. One way is to think of it in terms of paths, right? And the other way is to think of it in terms of simple neighbors. Now, if you think of it in terms of neighbors, you have to keep in mind that there are 2 scenarios that you will need to keep track of. The first one is the scenario where that node of interest is the middle node in this open triangle. And the other one is that scenario where that node of interest is one of the terminal nodes, right? And so those are 2 scenarios. The other way, so that's the neighbor's perspective. And so in this case, the neighbor's perspective involves taking, especially for the terminal case, the neighbor's perspective requires that you actually do one more path traversal. And so actually that's how it's related to the path perspective, in which you look for one path to 2 degrees away and ask if there's a path back to you or not, right? And that's how you look for these open triangles. Now, if you've heard of the term collaborative filtering, right? That's a product recommendation strategy, users with products. And essentially that's analogous essentially to open triangles, but not on a single partition graph, but on a two-partition graph, where you have users on one end, on one partition, you have products on another partition, and you're asking if this user bought this product and some other products, and another user bought that same product. Now it looks like these two users are kind of similar, right? But at least by that one. So you can look for these open triangles across products that are shared between users. And that's an application of the open triangle, not in the single partition setting, but in a bipartite setting. Right? And we'll get the bipartite graphs at the end as well. Okay, so the next notebook, so this is sort of the end of this notebook. It's difficult. It's also the most difficult part. And so we're going to move on to much easier stuff beyond this. Now, before I move on, though, I want to ask, are there questions so far? How are people doing? Is there any lingering thoughts, any questions that you're not sure of right now? How about in general about network analysis so far? Everybody okay? All okay? Okay, all right. Let's move on to notebook number 5. This one doesn't have an instructor and student version. And this is because this is meant to be, this was intentionally designed as the break after the hardest activity. What I'm going to show you here is how you can read in, how you can store network data and read it in from from one particular storage format. So run that first cell. As I was mentioning, now if you think back to the beginning, right? At the beginning, we talked about how nodes and edges are stored in network X, right? And so you have the node list. G.nodes returns you a list. You can have a two-tuple in which the first element is the node, and the second element is a dictionary of node metadata, essentially, right? The age and the sex and whatever of individuals inside a social network, or you can do other nodes and other metadata. And then edges are three tuples in which the first two are your nodes that are involved in the edge, and the third element is a dictionary of metadata. You can actually store this as a flat file, as two CSV files, essentially. One which contains the nodes, in which each row is a node, and each column represents the metadata that's associated with that node. And the edge list is a second CSV file, in which the two nodes are listed there, and the edge metadata is stored there. So I'm going to show you a very quick example of this. I have included inside the repository a sample data set that comes from the Divi bike sharing. So Divi is like Boston's Hubway, or like Divi is Chicago's version. What's New York City's? Like there's a lot of cities that have these. Does Portland have one? What's Portland's one called? Bike shed. Okay, yeah. So you sort of like get half an hour of free rides if you're a member between stations and stuff like that. So what I have here is essentially a Divi data set in which we have the stations and their metadata and the trips and their metadata, right? And so the trips really represent the edges between these stations and stuff. So if you open up, okay, let me see. Oh, well, okay, I do have to unzip that. So if you go to your GitHub repository folder, and you go into the datasets folder, and you unzip this Divi dataset. Right? It'll expand to something that's about 100 megabytes in size. And what we can do is we can actually load this into NetworkX by essentially iterating once over the node list and then iterating once over the edge list. Now the edge list is large, right? So it's going to be, it'll take a lot of time if you do this naively, but this is, but in any case, this is simply the simplest version, the simplest way of how you do it. So we load this into memory, and that's the edge list. Now that one's going to take a little while, and you'll notice that so we have the trip, and essentially the from station ID and the to station ID represent the nodes in the graph, right? As if we model it that way. So if you want to load that up into, so if you want to convert this into a network X graph, what you can do is you can initialize the graph as, as shown here, right? G equals nx.digraph. In this case, I'm doing a directed graph, not an undirected graph, because it is each trip represents one directional thing. Each trip is directional. And then what we can do is we can add, so in this example, what we're going to do here is what we're going to, is that we're going to first add in the nodes, and then we add in the edges bit by bit. Now this is the naive way. And what I'm trying to model, what I would, in this particular very specific example here, what we do is then we iterate over the trips rows, and then we identify the start and the end, and then we make sure, then because what we're doing is we're counting the total number of trips inside the, between every pair of stations. We want to keep track of this attribute called a count, which is initialized to 1 if the edge is not present already, or we add 1 to that count attribute if it's already present. Now this is the naive way of doing it, and run that at your own risk because it'll delay time. Instead, if you know your pandas well enough, you can do a group by on 2 things on the from and station together simultaneously, and you add the length of the resultant group, essentially. All right. So that's one particular way that we can do this. And if I'm going to run this, it might take a little bit of time, but eventually we'll get to the point where we can look at. Oh, there we go. Eventually, it'll get to this point where we can look at the graph structure between the nodes. So the density of a graph is something that we can query, right? Because the density is the number of edges divided by the total number of possible edges. And so we can ask, between these bike stations, how many trips are being taken between, how many possible pairs of start and destination trips are being taken divided by all of the possible ones. And that gives us a sense of whether this bike sharing station network is being fully utilized between every destination, or if there's a particular structure and pattern between the bike stations. So in other words, a fully connected graph is one that has a maximal density. That is, every edge is connected to every node is connected to every other node. And anything less than that would have a smaller density. So we can do that, g.edges. We can look at the total number of edges that are there. Oh, sorry. This was meant to be a live coding thing. And if we do len g.nodes, we'll notice that there are 300. Now, what is the total number of possible edges that are over here in this graph? This would be 300 squared, right? Because we can go from A to B, B to A, as well as A to A, right? So self loops are allowed. So that would be, what, 90,000? So num possible edges equals that. The number of edges in the graph is that. And what we can do is we can then ask density equals num edges divided by num possible edges. And then we ask, what's the density? I should have gotten this right. If I can verify that, okay, slightly different. I think the density calculation might be, I can have A to A and A back. Okay, somewhere there. We're about halfway in. We're about halfway into, we have, the density is about 0.5. That means about half of the possible edges that can happen between these graphs, between these nodes, are represented inside this graph here. all right? And graph density is an interesting thing because if you think about the synthetic social network that I had given you all at the start, essentially that was a synthetic graph that had a density of approximately 0.1. That means 10% of the possible edges are represented there. And that arose from me creating this synthetic social graph using a random graph model, which is in which I basically iterate over every pair of nodes, and I ask, and I flip a coin that's a biased coin that says probability of 0.1. And with a probability of 0.1, do I add an edge between those nodes, right? And so then, on average, if you did many of these graph instances, you'll get 0.1 of the edges, possible edges. All right. Okay. So I'm going to skip over this part over here because what I really wanted to show you here was how do you load in the data, and then how do you compute from there. And then from there you can actually then compute other metrics of the data. And so what we're going to do next is move into notebook number 6. So that was like whirlwind introduction to how do you load data from pandas into NetworkX. You basically do the for loops. Now let's go to notebook number 6, in which what we're going to do is we're going to try a new thing. Now this was the thing that I was telling some of you earlier on. This was my whirlwind of inspiration on the plane flight over here, where I rewrote the statistical inference on network data component. And so this here is a big hypothesis test. Experiment that I'm running to see whether this notebook is actually more effective than the previous iteration than I did before. All right, so I'd like you to load up notebook number 6 and run the first cell. Now, if you have an issue with that line, scipy.stats, because you don't have scipy in your environment, comment that out for now. We won't, when it comes to, and comment out that line, actually delete that line. Because the KS test and the normal distribution stuff, that only comes in at the end, and I can just show you that live coding. Okay, now I want to first get a feel before I move on. How many of you are familiar with stats, hypothesis testing, Bayesian inference, and stuff like that? Can I just quickly show some hands? Okay. All right. This notebook was not meant for you in that I've designed this to be a more hacker's approach. It's very not theoretical. So I'm not going to go too much into theory. I'm going to do, if you actually look at the end of the notebook, you'll see where the inspiration for this hacker's approach comes from. This very practical approach towards stats comes from Jake Vanderplas and Alan Downey. By the way, Alan is doing two tutorials tomorrow, computational statistics and Bayesian statistics. So if you're attending that one, you'll get to see, this essentially will be the introductory flavor of what he's going to be showing tomorrow. Okay? So very little theory, lots of practical aspects towards statistics. Now, for those who aren't don't consider yourselves very well versed in stats, here is my opinion or my view on statistics in a nutshell. It essentially boils down to two activities. We're describing data and summarizing it, or we're doing inference on it. We're seeing whether something could have happened purely by random chance, whether our data could have happened purely by random chance. Right? And those are basically the two things that we're doing with statistics. People who have deeper training in statistics probably will disagree with me on the minor details of this, but I think this is essentially what it's all about. And so when we talked about descriptive statistics, essentially we're summarizing the data. So actually, just now when we did this at the beginning of the class, we did some descriptive statistics. What were they? On graphs. What were some of these descriptive statistics? Centrality is one. What's another? Connectivity. I heard connectivity. Anything else? There's even more fundamental things, basic things. The number of nodes, the number of edges, right? This is our data summarized. And then with inferential statistics, we're asking then, did our graph data come from some particular random model of graphs, right? So if you think about random models, that's essentially, say, flipping of a coin, the number of heads that you get from 10,000 flips of coin, that's a random distribution. The distribution of the number of car accidents that happen in some intersection, that's another thing that can be modeled by a random distribution. And so graphs, if you construct graphs according to probabilistic rules, you can get some distribution of graphs and graph descriptive statistics, right? So if I create, say, the synthetic social network that I was telling you, edges are connected with some probability, then it's not necessarily true that I will always get, say, if I have 100 possible edges and my p is 0.0 and I have a p of 0.1, then it's not always true that I'll get 10 edges in the graph. Sometimes I'll get 8, sometimes I'll get 12, but I'll have a distribution of the number of edges. And then therefore I'll have a distribution of the graph density, and I'll have a distribution over the connectivity of each node and such, right? And so this is what we really mean by, so this is how random graphs are created, and then random graphs are then used for inference to say, if I had some data and I wanted to know whether my data came from that model or not, came from some particular model or not, I can use that model as the baseline for comparison, and that's for randomness, so to speak. Okay, so what I'm going to do over here, what I'm going to have everybody do here today, is we're going to look at something that's sort of within my realm. It's not 100% close to my heart, but it's about protein networks, right? In proteins, when we measure proteins, we can also measure what other proteins they're interacting with. And so what we get is this effectively a graph that has some distribution of connectivity, has some distribution of edges, and we want to know whether a particular model of graph construction could have given rise to the observed data that we saw inside this protein-protein interaction network. All right? So what we're going to do here is we're going to load in the data. So if you look at this cell over here, I'm just going to give you a very, very quick overview of what the raw data looks like. The first 2 lines are something. There's like headers. And then from that point onwards, it's essentially protein 1 with protein 2, protein 1 with protein 3, etc. Yes, sorry. This cell. Okay. Oh, the whole thing.
Are you on a different branch or something? Did you push it out?
I did. So this morning I asked people to pull that down from GitHub. Oh. Ah. Okay. That might have been it. Oh, yeah, that's it. There we go. My apologies. I think I forgot to push it back up to there. Okay, that's going to take a while, so what I'm going to do is I'll talk through it. All right? I'll talk through it. So everybody relax. Don't worry about more coding and stuff. My apologies for that. Should have double-checked that. Okay, so I'm going to give you so in another case, let's go through this as if this were another, like Notebook 5, tour through how you would do this particular thing. All right, so this is what the structure of the data looks like. There's proteins by index, and each row is essentially an edge. So I have the edge list stored. There's no metadata that's stored with the edge list, and there's no metadata that's stored with the nodes. And so therefore, I don't ever have to load in my node data separately and then do the same thing as I did with the previous notebook, right? All I have to do is add in the edges. All right, so I convert this into a pandas data frame. You can choose not to do this. You can choose to iterate over the file directly if you want. But this is just one way of doing it. And so, right, I have like my rows of data. And so with that, oh, sorry, let me go back up. So we run that cell. There we go. And I can verify that I've added in all of my edges and that it is of the same length as that guy, right? So the edge list is 2,277 edges long. Likewise, it's 2277 edges here. And so what we can then do is we can, compute some basic statistics of the graph again, right? Just for exploration purposes. And so we have the number of nodes and the number of edges and the density of the graph. In this case, what I've done is I've directly called the density nx density function rather than computing it on my own. And then, ooh, that's weird. There we go. What I can ask then is I can ask, what is the, so because a random graph that's constructed by the, probability of point something, that in that graph it has a characteristic degree distribution, right? The number of edges that, the distribution of the number of edges that each node has is characteristic, and it follows a binomial. Actually, I'm not gonna say anything wrong. I'm gonna choose not to say wrong stuff here. So it just follows some distribution, and that distribution is essentially repeatable. And so what we can then ask, is, does this distribution of edges, the number of edges, come from that same distribution that that random graph comes from? And if it is, then that random graph is a good model for explaining how this data came about. And if it isn't, then it isn't. So if I take a look and visually inspect the distribution of degree centralities, this is what it looks like for the protein-protein graph. And if I look at what it looks like for, sorry, let me run that cell again. If I take a look at what it looks like for an ER graph, it's going to have some random distribution. All right, so how then do we figure out whether a particular graph could have, so how then do we do the hypothesis test essentially, right? The procedure often is you pick a test statistic and you compare that test statistic that you have for your data under the model of randomness that you have. And so one statistic that we could use is, say, the mean of the degree centrality distributions. Or another statistic that we can use is the variance. And we can compare the variance under our data versus variance under many instances of a random model, right? And this is what we mean by a hacker's approach. We're essentially simulating what things would look like under randomness and gathering the test statistics out and then doing a simple comparison of my data versus randomness. So, for example, I can generate, say, 100 or 1,000 or even 10,000 random graphs constructed in the procedure that I told you earlier, and then I can grab, say, for example, my test statistic, if I define it as, say, the variance of my degree centralities, then within that graph, I can collect 1,000 or 100 or 100,000 simulated variants, and then compare what it looks like under randomness versus what my data is showing, right? And if this red line, essentially visually, if this red line was within some bulk of this blue histogram, then I'd say, all right, it's quite likely that my data came from this model of randomness. And if it was, but in this case, like we're saying out here, it's on the outside, it's on the outskirts of this model of randomness, and so it's very unlikely that we could have gotten it from this random model. Okay, so, and then there we have the hypothesis test done. in which we ask, what's the probability of seeing this under randomness or something more extreme? That's really all it is to statistics, inferential statistics. An alternate way of doing this, for example, would be to use a two-sample KS test, right? And a KS test essentially asks whether two distributions are identical or not, all right? And so we can look at a KS test between, say, two distributions that are supposed to be identical, and the test statistic and the p-value are going to both tell us that, nah, it's not really, the probability of these two being from the same distribution is pretty high. But if we do something that's between two very different distributions, the probability of it being, of seeing this is going to be quite low. And so if we do it for our degree centralities for an ER graph, or the random graph, versus the degree centralities for our actual data, we'll notice that, yes, they don't come from the same distribution. And so that's essentially how we can do inferential statistics on network data by comparing a characteristic descriptive statistic of that network against models of randomness, all right? So that's sort of the nutshell version. Again, I apologize for not putting this up. That was an oversight on my part. Thought I had pushed it to the remote repo, but apparently not. So I'm going to leave these notebooks. These notebooks are always freely available for you to download and take a look on your own. You can always play around with the code on your own as well, modify it, convince yourself of the arguments that I'm making inside there, and welcome you to download that. All right, so we have a little bit of time left. There is a notebook on bipartite graphs. I'm wondering, how's everybody's energy levels right now? Do you feel okay to go through it, or would you like to take a break, take an earlier break? I can do discussions of network problems that you might be encountering, etc. I'd like to give you guys the opportunity to direct this last portion. What would you all like to do? So if you're in favor of bipartite graphs, put your red sticky up, and if you're in favor of a general discussion, put your blue sticky up. Blue, red, 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 blue, blue. Okay. So I see more reds. So reds mean bipartite. So let's go through that then. So this is the last part. And I have not structured this one as a class exercise thing, partially because we've done sort of the hardest part here already in Notebook 4. So what I'm going to do here is I'm going to use this notebook as a way to introduce you to the idea of bipartite graphs. And so a bipartite graph essentially is a graph that models data, that models nodes that come from two very distinct groups. And you would never, the rules for creating a bipartite graph are such that in one partition, you never connect nodes with one another inside that same partition. The nodes are always connected from one partition to another partition, right? So here's an example from what we said just now, users and products bought, right? Users are never connected to one another. They are always connected to some other product, but they can be connected to other users by virtue of being connected to the same product, all right? And so that's how a bipartite graph is constructed. In here, I have an example of cities that my wife and I have visited. And so that essentially is another version of a bipartite graph where I've been to Vancouver, she's been from her hometown, I've been to San Francisco, she's been in Boston, and I've been in Boston. I should be here as well in Boston, right? Let me just check that. Yeah. And then she's been to Beijing in China, whereas I have many, many years ago, but I don't consider myself familiar enough, so I've not included that in this sample data set. All right? So now, likewise, we can look at the betweenness, centrality, the same metrics that we use for unipartite graphs, we can also use those same metrics on bipartite graphs. So for example, Boston as a city would be a highly connected, would be very highly connected to other, sorry, it would be one of those highly betweenness centrality, high betweenness centrality nodes, because by virtue of so-called many of us being connected to there, right? Whereas, and then for the use on the people side, right? We have different metrics of connectivity over there as well, because if you again think through how the graph is structured, you'll see if you want to pass a message from one city through a user to another city, you know, that's how this betweenness centrality metric would end up working. You can also look at the degree centrality, right? And so you'll notice Boston has a degree centrality of 1.0 simply because it is connected to every other possible user or person inside there, right? So the degree centrality metric works there. Now, there's an interesting thing that you can do with bipartite graphs. You can actually create a unipartite projection of a bipartite graph. And that's a good way of condensing down your data from a complicated bipartite thing into something that's a bit more easy to manipulate, which only has one partition. So, like I was saying just now, if I have the users and the products page, users and products bipartite graph, and I want to know what the network connectivity between users is as modeled by their shared number of products that they've bought, what we can do is we can say, take this bipartite graph and convert one partition to edge metadata, right? So I can say between two users, how many products do they share? And that can become the weight of the edge between those two users, all right? And so Network X also provides a function to do this bipartite to unipartite projection that can then let you do your network analysis back on a unipartite structure for which everything else that we've gone through today allows you to, well, everything else that we've gone through today becomes a useful tool that you can use for further analysis. All right? So I've included a few exercises over here and inside these notebooks. If you'd like to, you can take a stab at the last one in which there's the Divi bike data set. You may have to go back to the previous notebook and reload the data inside here. You can try creating the bipartite graph. If not, I'm happy to just walk around and talk with you, figure out, talk about some problems that you've encountered and all that stuff, or etc. But yeah, so we'll open up the time a little bit for that, and if you feel like you'd like to do, if you feel that you need to go to the restroom or take off early, by all means, please go ahead. But do not forget that there is a survey link for the tutorial, right? So we're constantly looking for feedback on how this works on the tutorials to improve it and stuff. So I invite you to do that as well during this time. But actually, so I'm going to finish off by doing one last thing. So I'm going to summarize what we've learned today. All right. The first thing that we've done is I hope you've all become familiar, a bit more familiar with the Network X API. Some people earlier on were asking about scalability issues. How many nodes and edges can we model with Network X? And my rough estimate is on the order of hundreds of thousands to millions is good for single core on your laptop in memory sort of thing. If you want to go any bigger, there are other packages like iGraph or Apache GraphX, part of the Spark distributed computation platform. So you can do that. If you're looking to store data in a network, there's actually this thing called Neo4j, which has Python bindings that allow you to store your data inside there. But anyways, that aside, we have gone through the NetworkX API, so I'm hoping you all have a better appreciation for that. The next thing that we did was we went through the algorithms. How do you think through a graph, right? How do you find paths? How do you find structures? And how do you model? How do you find interesting things, fundamental interesting things inside a graph, which can then be composed and used in higher order, structure searches and stuff like that. We also did a little section on loading data and visualization. And I again apologize. There's the statistical inference section, which I was hoping we could get people working on. But the notebooks are available, so please go ahead and try that out. Finally, with that, I'd love to connect with everybody on LinkedIn somehow, or on Twitter, etc. So all the information's up there on GitHub as well. All right. So all right, let's end early. I'm happy to talk with people. Please do fill in the survey. There was a survey link, and I'll bring that back up so that we can get feedback. I'm also personally always looking for ways to improve the content, so I'd welcome feedback from you guys here today as well. And yeah, thank you very much.